name is Zalen. I'm the electrical mechanical lead on Team 930, and I'm a senior as well.
My name is Greg Billadou. I am one of the lead mentors for Team 930, and this is strategic design. Launch break it. Let me click on the screen and make it work good.
With that clicker.
Now try.
Okay. So we're gonna start by introducing strategic design, how to set goals as a team, understanding costs, looking at the resources your team has, finding what is good enough for your team, and then utilizing community and commercial off-the-shelf resources. Then we're going to dive into a case study of the 2023 elevator for our team, and then as well with the intake for our team. And then we'll wrap it up with how to retain design knowledge for future use.
Oh, you went the wrong way.
There we go.
All right, so if you want to go back one slide real fast, just to that one. All right, so strategic design. In this presentation, we're going to take a little bit of a different approach because there are a bunch of strategic design presentations that exist for the FRC world. And I highly recommend you guys go watch those for things like always using rolly grabbers to pick up game pieces and a whole bunch of other like best practices. Mike Corsetto from Citrus Circuit 1678 gives this presentation every year. And so we're going to do something different than that. So I encourage you guys to go find that one and watch that. He's done it every year forever, so you can go back in time and watch it like 5 different times. Today we're going to talk a little bit more about like analyzing your resources and making strategic decisions. So I found this because I am a millennial degenerate and I was scrolling through TikTok. And there was this guy who was trying to make a CNC machine to mimic somebody's handwriting to fool their partner into thinking that it was actually them that wrote it. And he said this quote that really struck with me, and I had to go find it, which says, "You can't get to the moon by climbing successfully larger trees." Meaning, if your goal is to put a man on the moon, you're going to have to take a different approach other than just trying to find the tallest tree you can. This is not a dig on iterative design, which the presentation right after this will be about iteration, but it's trying to say that you need to start with the right idea before you start trying to reach the moon. And so the wrong idea, and we and I are very guilty of doing the wrong idea and spending a lot of time on it and ending up just being like, this is just not going to work. We have to go all the way back and start over. So I love this. Law of spacecraft design, I think is what it was. So, and that's where this comes in. The very first, this light actually turned right back on. Yeah, you want to go find that one? So it starts right off, bringing the right robot to the field. This can mean different things for different teams. And it's all about looking inward at your team and what resources you have available. What goals as a team that you guys have set. For example, in 2022, our goal was to get the autonomous award. And so every decision we made that season was, how does this get us the autonomous award? And that was, how is this robot the right robot for us this year? So setting goals for your performance and understanding how to achieve them. Another goal could just be winning, right? This requires in-depth understanding of your team, of the game, of how the awards are judged, etc. And so the biggest one we're going to talk about today is resources available to you guys. So I listed up some finite ones there: money, knowledge, machining time, bodies, student bodies, mentor bodies, etc. There's a whole variety of them, and learning how to balance them is going to be key here. So the big takeaway that we want to get out of this is managing and evolving your priorities based on the now to achieve those goals. It's great to have a plan for the season, but as if you guys have experienced, do we have any like rookie team members in here? Okay, from my own team, that's fine. We got a few here. Okay, so you guys will experience it next year. You don't count. No, I'm just kidding. Things don't go as planned, and it's being able to pivot and understand how the plan needs to change today based on what you see today to achieve your goals tomorrow.
Okay. So, first, probably a major part of it is being able to set the goals that your team wants to complete. And they need to be team decisions, so that means that every member of the team needs to agree on them, and that they must commit to them throughout the season. For example, as Greg mentioned, in 2022, our team had set a goal that we wanted to win the Autonomous Award, complete the Hexfect of the Robot Awards. And so as a result, a lot of our decisions were based on building a robot that had a lot of sensors, and autonomous functions to help us have a better chance at winning that award. So we prioritized having a fully autonomous climbing mechanism to be able to get that goal, and that worked out for us. And so those goals will drive your priorities. And when things go wrong or things go right, those priorities will constantly shift throughout the season. You also got to be able to understand the costs it takes for completing tasks. So there are direct costs, like I mentioned, like bodies, time, money, materials, resources. All of those things are limited, and you need to be able to balance those. But there's also opportunity costs. So, for instance, with time, if you spend some time on something, what could you have used that time to do as well? And that will evolve and develop throughout the season.
All right, so analyzing your resources, how you apply your resources during the season will define your success. Understanding your team's weaknesses as well as their strengths and turning them into strengths, turning your weaknesses into strengths actually is key, or planning around them. So the example I've got here, in 2016, we met out of a church basement. Our biggest piece of machinery was a Harbor Freight drill press where the chuck wobbled, so no straight holes out of that, and then a bunch of hand tools. Everything else was hand tools. But we had a sponsor that could do sheet metal for us. If we sent them CAD, they would send us parts, and they had a 1-week lead time. So we put so much of our resources into our CAD team, training them, getting them computers so they could do that, making sure that they can collaborate and build their skill set. So that then we got around kind of that tool limitation. We had to plan around this though, because if you've worked with machine shops or anybody that produces something for you, there's what's called a lead time, basically the amount of time between when you give them something and they give you something back. So when we got them the CAD, it took them about 4 to 5 days to give us parts back. We usually sent them CAD on Monday, and 9 times out of 10 we would get it Thursday or Friday. In a 6-week kind of time frame, which is less important nowadays. Now you don't have to bag your robot and you can bring it there. But back in 2016, you had 6.5 weeks. Losing a week to parts is difficult. Especially back then, we built 2 robots. So we had the practice robot and we had the competition robot. The practice robot came first. We sent that out, got it back, put it together, and figured out what we did wrong, right? Because we didn't have a robot at hand until that point. And so then we had about 2 days to go back, change everything we broke, everything we did wrong, send out the next set of parts for the competition robot and get it back. Back then, I was really, really, really into pretty robots. And so we also had the robot powder coated. I backed down off of that for the reason that that also had another 5-day lead time. So basically it took almost 2 weeks for our final robot. We worked backwards from there, meaning that because it takes 2 weeks to get the real robot, okay, and that's week, you start with week like 6, okay, 5, 4, and we'd have that sent out by week 5 or week 4. But we need to understand what we did wrong in the practice robot, so we need to send out a practice robot. So what that worked out to is parts, the robot needed to be designed and done week 3 of the build season and sent out. And anything that didn't get done then wasn't getting done. Picture on here is actually the very first part we got in 2016 that year. And that was our process for a handful of years before we realized that getting basically one iteration on your entire robot is difficult. And that'll be the talk in about an hour. And so we changed our process and got some more tools to work around that. But yeah, we did plan our entire season around this one company for 4 seasons there, so 2015 through 2018. Oh, there's some pictures. So yeah, if you actually go back, I forgot that we put pictures in here. So that first one that I showed you before, that was the 2016 robot. About 2 days, 3 days later, this is what it looked like. So we had to do a big jam session of getting it all assembled. Because like I said, we get those parts Thursday. I needed to send out the next version of the CAD on Monday. So we needed to test the robot. So this was about 2-3 days later. It's like 75% complete, but good enough for testing. And then the next day, we are actually testing it with some basic code to see how it operates. 2016, like half the game was just, can you drive over difficult things? Which as a concept is interesting. And so this was about like 4 days from that piece of sheet metal in the top left to robot in the top or the bottom right. The next day we put the intake on and had some like driver practice, and our driver immediately drove it into a pole and just bent it all up, and that was done, which was real neat.
So in 2016, like Craig had said, we only had a few available tools. So a big option for you if you have money is to look into commercial off-the-shelf resources. But there's also a lot of free resources out in the community. For instance, with programming, there's Word libraries that you can use to your advantage without having to program everything from code. So with each part on your robot, you need to decide whether it's worth designing it, fabricating it, or you could just buy a commercial off-the-shelf component of it. Like I said, there's a whole ton of opportunities available to you to use in the community. There's tons of vendors like Anymart, 50Bot, Rev. All those things offer options that can take a lot less time than some other resources.
And this is kind of those trade-offs. So Alan said, if you've got money, really it's if you have more money than you have time, right? It's that balance of, do I have or if it's not time, if I have the people to do this. Do I have the people to design an elevator and to fabricate it and to test it and to fix it and do all that? Or is that opportunity cost too high where they could be doing something else more important because I could just go out and buy an elevator? Obviously those choices aren't easy because nothing in here is cheap in FRC. Everything is crazy expensive, but it's kind of balancing those resources, making those decisions. That's a laser. So, what I like to talk about, and what a big part of the next presentation here is going to be finding what's called good enough. So, there's this concept in FRC that your robot is never good enough. It's never done. And that is true. But that's only true if you look at the entire season as like a single data point, where you're saying my robot needs to be better because it's not good enough right now. What you need to look at instead is kind of a timeline of things. Is your robot good enough today? It can be better tomorrow, but is today good enough? And so what that means, basically at some point you're going to have to choose between continuing to optimize or debug or add features and moving on to the next one. Okay, you can't spend all of your time building an intake. Your intake needs to be just good enough to get it to your shooter so that you can get that ball out. Or you're not going to be able to spend all of your time fixing and tweaking and making this look super duper pretty because your programming team's going to be really, really mad that they haven't been able to work on their autonomous mode yet. Okay? It's working on that balance and finding what is good enough for you right now. So learning how to determine when something is good enough and moving on to the next one is a strong skill, and it's difficult because we become attached to the parts of the robot that we work on. And I am guilty of that to the extreme. So don't worry, I understand. But it's something that you need to be able to take a step back and look and say, okay, I've done my part good enough for now. Good enough that I can hand this to the programming team and they can break it. And when they break it, now I know what I need to fix. Okay, it's this kind of iterative process of my laptop dying and me clicking the button and it coming back. This is all parts of the season, okay? So, like Aylin said, when should you buy something instead of making it yourself, or vice versa? When should you stop working on one autonomous mode and move to the next one? For people that were not rookies, so were participating last year, we had a lot of autonomous modes. There were a lot of things that you had to do. And it's understanding when this one is good enough for now, because what you should be looking at is what is going to give you the best net gain for your effort, for your time. And over time, you're going to get, it's what's it called? Diminishing returns, where you're going to be putting in a lot of effort and not getting a lot. You need to be able to find where those diminishing returns aren't quite as effective just yet. Okay. At some point, yes, you're going to be optimizing for half a second or more time on your autonomous mode, but you need to make sure that you're not doing that until you finish the autonomous mode that like you actually need to have and you haven't started yet. And then the one that's sad is when should you stop fixing what broke in the last match and focus on getting your robot out to the next one. At the end of the day, we get 10 matches at a competition, okay? I'm not gonna talk about how much that costs because that's really depressing. You need to be out there on the field with that robot. And maybe that means, and happens to everybody, where one part of your robot just isn't working right now. And you can spend time fixing it, but at some point you need to make sure that you're out there playing that match. And maybe that means you're not picking up game pieces. Maybe that means you're playing defense. Maybe that means that you're only scoring on the low goal. We've had that where our elevator got broken and we just need to score low because we need to be able to play. What this means is don't take your robot entirely apart, not knowing if you can fix it before the next robot just to fix one small bit of it, okay? This is all part of that finding good enough, which is hard, which is difficult, but important. And yeah, being able to step away and learn when to move on is hard. I struggle with it still. This is my 18th season of FRC and I still struggle with it very recently. You love the laser button. All right, so we're gonna talk about the elevator a little bit. This is my talking block, so I get the button. So we're gonna talk about the 2023 elevator. It's over here. Unfortunately, these tables are higher, so it's kind of hard to see, but we decided very early on that we were going to build an elevator at like 45 degrees to go out. I got a little GIF in the corner there of kind of the original concept for this design that we had basically the day after kickoff. We're like, okay, at a high level, this is kind of what things are going to look like. It can reach all the points that we need to score. Great. It checks all the boxes. We need to figure out how we're going to do it. How difficult is it going to be? Is it worth those costs? 930 has an existing elevator design actually from 2018 and 2019 where we designed our own bearing blocks basically. So the big part about your elevator is it needs to go up and down smoothly and not fall apart. And in 2018 or 19 we had these, basically they're plastic bearing blocks that look like H's. You can kind of see them right here. That were cheap, easy to put on. You could build them with hand tools. In 2018, we actually did build them with hand tools. We just bought the correct widths from McMaster and then used bolts to make little H's. Obviously, that had tolerance issues when you're just hand drilling holes into pieces that need kind of a decent amount of tolerance, but it worked for us in 2018. In 2019, we improved on that because we got access to a CNC for the first time that year, and we spent all of our CNC resources that season on making these stupid little plastic blocks. We had a mentor and a student that basically all they did for like 3-4 weeks was sit there and try to figure out how to machine plastic properly, because machining plastic with a mill, it expands, it flexes, it deforms, it's a problem. And it takes a lot of resources, but they got it done, it went on there, and that robot went on to play nearly 100 matches. That was the season we went the furthest. It played, I think, 70 official matches, because we did 3 events, champs, and we made it to Einstein that year. And boy, all we had to do occasionally was like take a little thing of like, it wasn't WD-40, but grease, and just kind of spray up and down, take a rag and wipe down the tube rail, and that thing held up great. that was what we could, that's what we did back then. And so we had to decide, did we have the resources to do that again? Okay, so 2019, that mentor is out in California now building rocket ships. That student defected to Moore as a mentor now. So I like to harass him, that's fine. So we lost all that knowledge, okay? Was it worth it to spend all that time? And we've started to invest more in our CNC design. We spend a lot more of our robot is built in-house. I said 2016, we used to send out our entire robot. Starting in 2019, we did the entire robot in-house. And so we do everything on the router and the CNC mill that we have in the shop. And so we don't really have the time to invest in just making these little blocks. So we had a choice between doing that or buying something, okay? So like I said at the bottom there, also, probably the biggest thing with this elevator was it was kind of unorthodox. Most elevators you see today are all, they're all 2x1s and they're all oriented kind of together, right? So they keep up a really thin space. Ours was the reverse. It was 2x1 stacked like this. So it was really, really wide. It took up a lot of space. So we had to choose. Did I get the arrow right the first time? I guess so. Okay, so quick, like what I just described there. If we did the 2019 way, material cost is pretty low. You just buy plastic from McMaster. The design cost is a little bit medium. I said that because the elevator we designed before was a straight up and down elevator. This is now an elevator at 45 degrees. Do we know if it can handle that? Do we know if the plastic's not going to just slowly open up? And the time cost of that is pretty high. Machining our own parts, dialing in can take man hours and machine hours, and we only have one CNC. So, risk analysis there. The elevator really isn't the show of the robot, right? It's not the main actor, it's the supporting actor. It just needs to get the important bits of the robot to the right places. It just needs to work. Okay, it doesn't need to be fancy, just needs to be fast, robust, and maintainable. And so, kind of labeled it there, high risk, low reward. Again, it just needs to go fast, and the hope is we never touch it again once it's done. I already forgot which arrow I was supposed to press. So, if it wasn't obvious what I was alluding to here, we decided to go with a COD solution. We did end up modifying it, and it's over here, we can look at it later, but you can kind of see it in here. We wanted an open top elevator design so that our arm could swing over it. The danger there is that you don't have that cross rail, and if anything flexes, your entire stage can just pop out and like fall off the robot, and that's not cool. So we bought these bearing blocks from Thrifty. Everybody sells almost identical bearing blocks. They were just a little bit cheaper, and we like their customer service a little bit better. And we modified them just a hair. So you can see in this progression pick here, so those are the bearing blocks. This is kind of the final product at the time. What we decided to do is to take this bearing block, extend the shaft that holds this bearing, and then put a piece of plastic on the other end to like fully capture the tube. That cost us a little bit. We had to add an extra tube onto here because if you have two bearings, they have to go past each other. And if they're going around and capturing the whole tube, it's not gonna happen. Does this thing go up? We're doing really good on time, so I don't mind pulling this. So I'm gonna turn it this way, and yeah, let's give it a shot. So, okay, you're super tall.
Yeah.
So we're just gonna get up as much as we can. And Kaden, you're gonna stand where I am because you're blocking everybody.
Yeah.
I'm gonna shimmy because my team's already seen this robot. So the bearing blocks I'm talking about, you can kind of see them right here, and right here. They fully capture these rails. So that if this thing flexes, yeah, you guys can get up, it's fine. If this thing flexes, it can't pop off. It would actually have to shear the bolt here or tear the plastic or something. And the cost here with doing that was weight, actually. We had to add a second rail. So like usually you only see this stationary rail at the bottom, this white rail here, and then the carriage. But because we wanted this design because the bearings have to pass each other, we had to add another rail. So this is now like a 2x2 kind of design. So a little bit of weight. fortunately, it's really thin metal. I think it added like half a pound to the robot. Once we did that weight analysis, it's like, oh, that cost is actually really, really low. And that lasted us the season. You can go ahead and put it down. It wasn't as maintenance free as I like to describe the plastic blocks. We did have to replace, we replaced the bearings because they're taking a load that they don't usually take just because they're at 45 degrees. And the plastic wall that we added was slowly turning into a semicircle as the robot was shaking. It was bending that plastic. So there was maintenance there, but we got what we wanted. Thank you, Kate. Yeah. So we took a cost design, we modified it a little bit so that it fit our requirements, but we saved all that time on machining. These blocks are really neat. Bottom, didn't really have to touch them outside of what I just described. And allowed us to put our design resources into the things that matter. This whole guy, the ground intake, all of that, the elevator gearbox itself actually moved it up and down. We could spend our resources on that instead of this relatively unexciting bit up there. Everyone likes the exciting parts of the robot, right? So, robot is pretty complex this year, as you saw. It's got 3 degrees of freedom. It's got the elevator that moves the arm up and down. It's got the elbow, or the shoulder, I guess you could say. And then it's got the wrist there. This is actually, so I'm describing this to you guys, and I'm gonna ask you a question about how you would approach something. So, pay a little bit of attention here if you have it on. So, we had this robot built. I put on here a picture here, February 11th, 6 p.m. That was the week before Sussex, I think. I think that's a Saturday before Sussex. So if you guys go to the Sussex competition. Basically, that February 11th, the mechanical team picks the robot up, walks it to the carpet, puts it down, and says, programmers, this is yours. Okay, and they walk away. We need to find positions for intaking and scoring. There are positions where this robot can run into itself and tear itself apart, right? Because it's this arm swinging, it's going up and down. At this point, we've never run the top half of this robot, so we had no clue if this intake was going to work. And if you're paying close attention, you'll notice that it's different than the one that's on the robot. Spoiler, it didn't work. We also need driver practice, okay? Like, you could build the best robot in the world, if the driver's never driven it, it's not going to work. We want to be able to make the elevator go faster because a faster robot scores more points. And we need to find the weak points. Because all of that there, as you can imagine, there's a lot of weak points. Now it's hard to see, and I didn't put it on a bullet point here, but also half of this robot is held together by cardboard. Okay, we use a product called Masonite. It's really just compressed cardboard. And we use that for all of our prototyping because we can laser it, put it together, it takes like 15 minutes. If you can see the robot here, these side pieces, right here, were Masonite. And these side pieces hold the entire top half of the robot. So basically this entire elevator arm, everything was held on by 2 pieces of cardboard, the base of the robot. Okay? So, I have to check, is this the part where I ask you? Or, yeah, okay, I have a little bit more information. I always forget this part. So we have a couple options here that we have to weigh in our strategic decision-making process. Do we focus on, you've been handed the robot. Mechanical team says they're done, they've wiped their hands, they've gone to Culver's. Do you focus your time on making the elevator and arm as fast as possible? Do you focus on getting driver practice as soon as possible? Do you focus on just running that mechanism up and down to find the weak points? Do you find the positions, et cetera, et cetera? Before I ask you to pick an option, what questions are you asking here? Like, what more information do you need to know? And I'm thinking of them while I ask you. Go ahead. Exactly, that's the big one, time. What time in the season are you? And corollary to that, so I said February 11th, the week before our Sussex Week 0 competition. So how much time do we have, and what are our goals for Sussex? Okay, like Aylin said at the beginning, you set goals for the season, and you set smaller goals for your next competitions. So what are the goals that we had for Sussex? Any other questions here? Yes?
Is your drive team gonna be new, and how experienced are they?
Perfect, yep. How much time do you need to dedicate to some of these resources? The drive team's a great example of, have they ever driven a robot before? Are they gonna need more time? It's the same thing with the other parts. How often has your programmers worked on tuning an elevator? How well versed are you in like the positions that this robot can get into to brake itself? All of that kind of stuff. There's a lot of unknowns. What would you guys start your focus on? Because all of these are pretty important. Let's assume that the first thing that they did was get positions for scoring. Okay, they found the height on the elevator. They found a good enough on the arm. Okay, so now you got these positions. What's the next thing you guys do? And there's no real wrong answer here. This is part of the learning, part of the growth, and understanding what is best for you, your team, and your robot. Go ahead.
Make sure it won't destroy itself.
Sorry?
Make sure the robot won't destroy itself.
Make sure it won't destroy itself. Yep, that's a good one.
Finding your weak points first, because I would say you can't make the elevator and intake as fast as possible if it's going to be weak.
Okay. Any others? All right, so I think it's on the next slide, we'll see. Oh, these are the questions we asked. And look at that, the very first one. What time of the season is it? How much of the robot is prototype versus real? How competitive does it need to be at our first event, which in this case was Sussex? This is the one that I want to highlight here today. How much do we want to learn before we break it? Okay, so you pointed out that you want to find the weak points in the robot first. Part of finding the weak points is breaking the robot, correct? So there's a trade-off there. If you find those weak points and break the robot, you stop at that point. You have to go back and fix that stuff now. What do we plan on iterating on next? This is another big one. This is a little bit forward thinking, like what is the next thing we need to verify and work on? In this case, it was the intake. Like I said, we didn't know if it worked. So we needed to test it and see if it was gonna work and see if we need to make any changes. And then what upcoming changes are going to invalidate anything we learn now. So in this case, like I said, half the robot was still masonite. There are some things that just aren't worth testing because it's not the real robot, okay? So I think, next slide here. Apparently we had a title slide halfway through. All right, so February 11th, 9:30, like 1 or 2 meetings a season meets really late. So don't be spooked by the timestamps there. We basically say, all right, this is the big day. We have a lot of progress ahead of us. We're gonna take advantage of that. We've got some momentum. So 10 p.m., they were trying to find those positions. You can see it's going really well. It's slamming the robot up and down, and they're trying to tune that kind of stuff. About 30 minutes later, they found those positions, and the slow march to awesomeness, it's going. It's thinking about it. I blame Ed, because I think Ed's in the room. There he is. He's in the picture. It's going. Here we go. We're driving. And we scored. All right, is that a regional winning robot? No. But it scored. Those positions were verified, and it went through all the motions on its own. 30 minutes later, so after we've done all that, this is my favorite GIF ever. It falls apart. It just snaps. Like I said, the entire top half of that robot was on 2 pieces of cardboard. So our driver was like finally like, all right, I'm gonna get driver practice now. We verified that the positions, we verified it can score. We're gonna see if we can intake. And the reason he's doing this dance here is because he was chasing that game piece. Because we had a horizontal roller intake at first, and when you don't hit it centered, the game piece bounces away. So he's chasing it around. He gets all that vibration, and it just broke. I cut off the end of this GIF because it's good, but I don't like having it. All right, it wasn't important. But at the very end, there's a really great like office style zoom in on our student lead who's like, if you've watched The Office, you know Jim will always kind of stare at people. It's really great. It just turns, zooms in right on Abby as she's just like. So 11 p.m., we're done. Robot's broken. But we have positions, we know it can score them, we know the intake is not great. We now know that we can no longer survive on cardboard, we need to move forward. So a week later, you can see we've got a new intake on there. And we're tuning positions here, and we're speeding everything up a little bit because you saw the first game piece score was very, very slow. So that was lunchtime. By 5 p.m. that day, this was a Saturday, Sussex is on Sunday. So 5 p.m. it's scoring a game piece with relatively decent speed. It's still probably, like a 5-second scoring cycle, but for Sussex, for week 0, for when you're just trying to experience a competition, this was good enough. And then a couple hours later, we're doing full driver practice where our driver is just driving around, picking up game pieces and scoring. Our robot was ready for Sussex. It wasn't regional ready, but like I started at the beginning of this presentation, it was good enough for today. Everything was kind of growing as a unit. We weren't lopsided and saying the autonomous mode scores 3 game pieces, but the drivers never touched the robot, and also the intake goes really slow. Everything moved up together. And then just showing this, so Sussex speed, your GIF you already saw, good enough, that was not good enough for our first event, which was Midwest. We sped it up, this is about 2 times faster, and then we did it again for our next event, Wisco, and we sped it up about 2 times more. It wasn't worth the time to get to this speed for Sussex because there were so many other things we needed to fix, so many other things we needed to verify. It's that idea, is it good enough? Okay, I'm done. I can drink my coffee.
All right, so now we're gonna take a look into case study of the 2023 intake and kind of adapting to the game strategy as it evolves throughout the season. So the ground take here on the robot was made so that we could intake pieces from the ground a lot better than a manipulator. Because with our manipulator, we can still do it, but it's kind of risky with our long arm coming down to get game pieces. If someone were to hit it, it could break. And so with the time that we had allotted, we wanted to work on a separate mechanism to be able to help us with that. So kind of design-wise of it, we had used 4-bar intakes in the past, so like 2020 and 2022, we had all used 4-bar intakes. The other thing is that currently there was no pneumatics on the robot, so we wanted to avoid pneumatics and extending and retracting the intake. But overall, through everything, we knew that if something were to go wrong with this mechanism, the rest of the robot could still function by itself without it. So with that in mind, this was our first prototype for our intake. So it used 2 rollers right next to each other going in opposite directions to grab the flange of a cone. And then the idea is that it would rotate the cone upwards so that the manipulator could come down and pick up the cone from there. And the issues with this was that it was very, very complicated, probably too complicated for what we needed, because it relied on either a lot of buttons for the driver to extend the intake, rotate the cone upwards, and then bring the arm down, or required a lot of programming by using sensors to sense the cone. So with that in mind, we looked to make some changes with the design. So what we did is we added a back roller to our intake. And the reason for doing this was around week 3, week 2.
We had just competed at Midwest.
Yes,
And so
yes.
there had been 2 weeks of competition now, and we came back and had some lessons learned.
Yep. So we saw a high tide. In qualifications, what they do is they score a couple game pieces high, and then for the rest of the match, they only score cubes in the low hybrid area in order to get the link RP. So we looked to try to do a similar thing in order to get more RP in a match. So we converted the ground intake into a hybrid only cube intake. So we added that cover over the top so that we could intake the cube, and then we just extended it again and outtake, and it would shoot the cube out. The issues with this is by the time we got it working, it was around the Wisco regional, so around week 4. And we noticed that we really needed to score high for all of our qualification matches in order to win our matches. So we weren't able to use the intake pretty much whatsoever. So at that point then, we still had that space, we still had that time. And we modified the intake so that we could just bring the manipulator above the intake and create a direct transfer from the intake to the manipulator. And this made our cycles a lot faster. We were able to reduce the amount of time it took for us to get a cube. So in champs, when this was working, we were able to do fast cycles between the edge of the substation where the human player would flick out the cube and to the grid where we could put it anywhere we wanted. We could put it high, we could put it mid, we didn't have to put it low.
And I just want to highlight the phrasing that Aylin used there, when it was working. This goes back to the concept of your robot needs to go out for a match. And so there were a couple matches where the little 550, and I think Aylin's got one, the sensor cable stripped, and so we needed to get in there and resolder, and that thing is deep in the robot. It needed to go out for a match. Going out was more important than getting that 100% solid.
Yeah, and because this is a mechanism that is not necessary for the function of the robot, if it wasn't working, we could just use the rest of the robot just fine. It might not work as well, but we were still able to fall back on the solid part of our robot. So in the eliminations of champs, like Greg mentioned, the sensor cable on our extension motor of our intake got damaged, and we did not have any time to really fix it. So we really just locked everything down and used the rest of the robot, and we were still able to be very competitive in the eliminations of champs. So kind of concluding it, if you have a separate mechanism that isn't critical to the function of the robot, you're able to adapt to the game strategy as it evolves throughout the season. So in the first couple weeks, every cycle mattered. So if like a cone was dropped, a mechanism to be able to pick that up and transfer it was useful. But when the link RP became more obtainable around the mid competition season, a hybrid-only cube intake was useful as well. And then finally, when champs came around, being able to do as fast cycles as possible and having the flexibility to score anywhere was very valuable. So to wrap things up, we're going to talk a little bit about retaining design knowledge. So a lot of things can happen is that as upperclassmen eventually leave the team, design knowledge can be lost. And so here are some ways to retain that, and then also how to prevent issues from happening in the future. So this past season, the team made 2 large changes to help us with that. So the first thing is we created a kind of official design review checklist. So after a design is completed, there's a checklist here for them to go through and make sure that those topics are covered and looked into the design before it is approved. So for example, we have a section for all designs that's gone over for any design, and then we have specific sections for different subsystems, like if it's a drivetrain, if it's an elevator, if it's a shooter. And this helps us to avoid like something missing. Maybe there's not bearing retention screws and people forgot to bring it up. At least it's on the design review checklist so that it will be covered. The second thing is we also implemented what we call a design lessons presentation, and I'm going to explain that through an example. So on the ground intake, the Neo that spins the rollers, which is right up here, yep, that one right there. During IRI in the eliminations, the shaft sheared off of it. So I have it right here. You can see how there's usually the shaft right there, completely just sheared off. And that caused our ground intake to instantly become not usable. And there were definitely some flaws in the design that could have been different to prevent this issue from happening. So here is what the design lessons presentation, here's one slide for it. So we described the design and we described the issue. So the issue was that the shaft sheared off. And the lessons learned from it is that he learns that on the new 550, the shafts shear off really easily if they're put under constant tension, like if there's a belt on it, or if it's also just exposed. So what are a couple ways that our design could have been different to prevent that? Anything?
How do you guys protect your motors?
Yeah, so you can see in, we found some pictures of what other teams have done, where they have like standoffs or some housing to go around the motor to protect it. And that probably could have prevented the issue from happening. Another thing we could have done is on the new 550, there are some holes in the back of it. And there are a lot of teams that actually use, because the outside of the motor spins, they use those holes to actually attach it. And that won't break off. It's sturdy, it's strong, and if we would have used it in scenario, it probably wouldn't have broken. So this design lessons presentation allows us to put the lessons we've learned from design so that newer people, when they are shown the presentation, can kind of have that in their mind when they're designing new components.
All right, you want me to do the recap? All right, so we'll have time for questions after this. Strategic design is going to look different for your team. Depends on your resources, depends on what your goals are. But those goals will change throughout the entire season. You'll have this overarching goal that you guys as a team work on, but the stepping stone goals that you do to get there are going to evolve from day to day on how you reach those points. Utilize community resources and COTS resources to your advantage. There's the Open Alliance now, which has 100 plus teams. The Discord still exists. I think they're about to get rid of it, unfortunately, but Discord still exists. I just lurk in that Discord, and I just, once a week I'd go open each one and scroll through and see if anybody did anything interesting. Use that to advantage. You don't need to reinvent the wheel here. And then cross components. Manage your priorities. Remember that it's really easy to become attached to what you've been working on. Remember that you are a team, and this robot is more than just your intake, for example. Like Aylin described, this ground intake was on this robot before we went to our first event. It was not used in a qualification match until champs. It grew over time as the resources for it, the requirements changed, as our understanding changed, and as it just got finished. It's important to be able to look at the bigger picture for your team. And then look for ways to kind of retain that knowledge. Like Aylin said, seniors graduate, mentors realize that this is a lot of time, they don't have that kind of time. Find ways to continue the teaching of everybody as it goes through, so you pass that knowledge on, so that you're not restarting every 4 years. All right, anybody have any questions? And you guys can really ask about anything here, it's all cool.
Just pure curiosity, out of comes to the blocks of plastic these back in 2018 used. Do you know what the reason was for CNC instead of 3D printing?
So, and I'm just going to restate the question so it ends up on the microphone. The question was, in 2018, our bearings, why did we CNC instead of 3D printing them? The quick answer is we didn't do any 3D printing back then. The secondary answer is we actually picked a specific material, UHMW, for its, there's a better word than slipperiness, but I forget. It's level of, it's coefficient of friction.
Yeah.
There we go. It has a very low coefficient of friction. This season, 3D printing it would have been risky because of the 45-degree angle. All those forces would have now been on this little flange. But back then, it might have been I would have, if I were doing 2018 today, definitely would have considered 3D printing, because that's become such a bigger part of our team recently. Back then, we did none of it. It's really grown in the last 4 or 5 years. It's crazy. Other questions? I have a question for somebody who's paying attention. It's entirely unrelated. Does this presentation end at 11 or end at 10:50? Does anyone have the schedule? Oh, okay. We got 10 minutes in for questions. That's great. I did this exact same thing last year and really made my presenters upset when I rushed them. so I just rushed myself. Any other questions? Yes?
What do you think your most useful automated tool is between a laser cutter and a CNC stuff?
Sure, so the question is, what do we think our most useful tool is? And the examples he gave were between like the laser cutter and the CNC. Honestly, so the big tools that we use, we have a laser cutter, we have a Amio router that we got this last year, we have an array of 3D printers, and the school has a Haas CNC mill that we used to use for many years. I think it changes during the season. Like honestly, we probably get the most early value out of the laser, right? Like speaking for myself and a little bit of the team, we're pretty bad at the really like basic prototypes. Like I'm not good at teaching it how to take a bunch of 2x4s and screw them together and get something valuable out of it. And so we do a lot of our prototypes in CAD and laser them. Because boy, am I just terrible at that. And so we do a lot of prototypes in CAD, but after that, mid-season, the router becomes really useful.
Yeah, and I'd say the 3D printing has definitely grown to be a very major part. Like the gears we use in our manipulator, they're 3D printed. The whole system for holding our arm in place is all 3D printed. And it allows you to create pretty complex pieces while also being pretty cheap and inexpensive to make.
Yeah, I think 3D printing is great. The Amio, if your team can afford one, which they're only like $3,000. I forget. They're pretty reasonable. We did everything on it this year. Prior, we used the Haas CNC, and boy, a CNC mill is really, really cool if you're doing any sort of 3D milling, but you don't do that in FRC. You do what is called 2.5D milling, basically just XY with like a thickness. And that's so much setup, and it was such a pain. The Amio router is great. We did everything in it this year, and it comes out really nice. But really, I mean, the big thing with those tools is just understanding your knowledge of it, like how many kids you have or mentors that know how to run them, and then the time. It's like 3D printers, the biggest thing there is like if you don't have a bunch of them, they take a while. Now you can get one of the bamboos, and those are super fast these days, which is really cool, but even still, you're printing a lot of things. You gotta kind of balance and manage those resources. What else we got? Yes.
What was the reason for using masonite over wood?
We use masonite mainly because we have used masonite. It's kind of just a historical thing at this point. It's what the school used for many years that our kids learned the laser. The laser is a school resource. We don't actually own one in some classes teaching there. But these days, honestly, it holds up pretty well when compared to like plywood.
It's a lot more like the grain of it is very consistent. It's like tiny particles of wood. Yeah, and I think it lasers a bit better than wood, plywood, or wood would be. You can get it in pretty thin, like 1/8 inch thicknesses. So
I know. I think what's the other popular lasering wood? There's a word for it, and I'm always bad at it. It's kind of, I don't remember, but it's also popular. But like, I think the colloquial term here is hardboard. So you can go to Home Depot and just buy a 4x8 sheet of it. And so we just go buy a few of them. It's like $15 or something. Yes. Yes. So I think that's technically what masonite is. I know there's another type of wood that's very similar that is very popular with prototyping and with laser cutting enthusiasts.
Yuan? Yuan?
Maybe. But yeah, no, we usually go buy a couple sheets of 4x8 and use those during the season because it's like $20 and we just cut them. If you went to MROC this year, the entire floor under the field was actually those sheets of hardboard as well, because otherwise the school would murder us because we damaged the gym. Just fun facts. Other questions? Awesome. Well, thank you guys for being an interactive audience and answering some of our questions and asking some yourself. You've got a few minutes here. If you want to take a look, or if you want to just go on to your next one, or if you want to talk and ask questions, go for it. Otherwise, thank you guys so much.